If you have a polynomial written in proper order of descending degrees, so n minus 1, all the way down to the constant term, Descartes' rule of sign states that if that the number of positive real roots is going to either be equal to the number of sign changes or less by an even number. So I want to look first at the easier part of this to prove. It's pretty intuitive. So the even number part. So for both of these examples here, we're assuming that the first term, the leading coefficient, is positive. And so if the constant is positive, well, then it's going to be somewhere uh, on the y-axis. And we know because of the behavior of polynomials that if the leading coefficient is positive means that this is going to rise from right to left. It has to. So what are the possible numbers of roots that could come about? Well, one is none. It just does this. Maybe it makes a bend and there's a couple of imaginary roots, but we're not worried about that right now. So there could either be 0, or it could come down and do this, but that's multiplicity 2. That's still considered 2 zeros, even if they're a repeat of the same one. Or it could come down and do this, in which case it's still 2 positive real roots. Or it could come down and go up, and come down and go up again, in which case that would be 4. But notice, because of the fact that every time it goes down it has to come back, that's going to create increments of 2 zeros. And so there couldn't be 3 positive real roots, for instance. So this would be the scenario for the possible number of real positive roots if this is positive. If it's negative, well, then the y-intercept is down here below. And again, it has to rise. So it's either going to have 1 positive real root, or it could come up, and again, it could bounce. So that would be 3. Or it could not bounce. It could do this. It would still be 3. Or it could come up and do this, and again, so that would be 5. It has to increase by 2. So in either case, the possible number of real roots increments upward by 2. I want to look at kind of the intuitive side of this for a little bit before I continue on with the whys, the proof. Um, so I made a polynomial here that obviously, and I'm assuming you know something about polynomials, which is why you're watching this. You know where positive and negative roots come from, as well as imaginary roots. And so this clearly is going to have only negative real roots. There's not going to be any positive ones out here. And we can see why. This is where they're multiplied together. So when we look at this, that's just this graph. They both are. But in this form, we can see the y-intercept is 6. And then if we think, as we go on past x equals 0 to x equals 1, x equals 2, and so on, well, these are only going to get bigger. This can only go up. There's no way it can ever do anything but go up. With no negative to force the function back down, there's no way it's going to get down and reach the x-axis and produce roots. So there aren't going to be any positive real roots with this polynomial. Now over here I have the same thing, but I'm contrasting it with this polynomial where I do have a negative, and it basically dropped this enough units down to where the y-intercept was below the x-axis, and now we do have a positive real root. That's just one example of how negatives can create positive real roots. And here I did it simply by just changing uh, these two numbers, and it of course took a negative. Now the same kind of thing would happen if I had maybe made this one -2, and then again we'd still be at -2 at the y-intercept, and then as we continue on to the right to the x's, um, then maybe it wouldn't rise as fast because of this term, but ultimately these two terms would win, and this term always ultimately wins. So anyway, that's just an example of creating positive real roots by simply changing a number. But what I want to look at right now is the idea of taking a polynomial. This is the same one, but I'm going to inject a positive real root into the situation, and we'll see the effect of it. And so this and this are the same, it's just multiplied out. And notice that we now have one sign change and one positive real root. Um, and so our x-intercept is -6, and we have another negative term here that, maybe that's responsible for making it go down a little bit before it went up, but ultimately these are going to win, and it's going to have to go up and create a root here. So I just want you to appreciate that negatives are absolutely vital to have any positive real roots. And you could do the same thing by, making the making this positive and then experimenting with, this, or I mean, making this negative and making this positive. But there's not gonna be anything new that happens. So you can experiment with stuff like that on your own if you want to take it further. But what I want to look at right now is this is the same thing I did here. It's just the same multiplication, but the difficulty of injecting a positive real root into something that in this case has no roots, and then getting to this and seeing, okay, there's one sign change. It went from positive to negative where there were no sign changes before, and we know that that was created by a positive real root. But then the discouraging thing is if you try to experiment with this, you're going to see that you're going to have like terms that are combining, and they could go either way. And between the coefficients being in there and the like terms combining, it can be a mess. And so I used a way to cut through the crap and get to where we can see exactly what's going on.
Notice when we inject this positive root into this polynomial that has no roots, just the nature of polynomial multiplication, well, this is going to multiply all of these terms and create this, and there are no sign changes created by this. Well, this number is what's going to cause the sign changes. And notice just the way the like terms combine, we do the -1 times this, so you basically create that, and then it slides under here. So if you think about it, we're multiplying this and we're sliding it under here. And then same thing with when we do -1 times this, and that's going to slide under here. We see that here. And so just what I'm going to do right now is I'm going to leave out all the variables and all the coefficients, and we're just going to look at nothing but pluses and minuses, and we're going to follow the pattern. So I'm taking this negative, and I'm going to do this. Just it looks kind of like we're going to do synthetic division, but it has nothing to do with it. And then we have 4 pluses here, so I'm just going to put those, and then I'm going to put a line here. It's kind of like, again, like synthetic division, but has nothing to do with it. And what we're going to do is just follow the pattern I was just talking about. We're going to do a negative times a positive and put it under here, which is exactly what is going on here. Then negative times a positive, put it under here, negative times this positive, put it under here, negative times this positive, put it under here. And then we think about combining like terms. Well, this would be a plus. These could go either way because remember, we're not looking at numbers right now. But what is forced? That's what we care about. Well, this one is forced too. So think about there were no sign changes here, and we followed the pattern of multiplication, and we see that these two have to be. There is now one more sign change. We went from plus to minus. That has to happen. That will always happen with this, just because of the pattern. And one thing we can do is kind of look at how it was before. Notice there were no sign changes, no sign changes, but here's a sign change. And because of the nature of multiplying by a negative, there will always be a new term that is different than, well, I should circle that one. There will always be a new term that is different, a different sign than what was at the end of the previous one. So what we're going to notice is a pattern where multiplying by the negative, aka uh, a positive real root, it preserves the number of sign changes that we had up to here, and it always injects another one. So it has to create a sign change. Now, notice something interesting here. These three can go either way. So this here, I mean, they could have all just been, pluses, and we got one sign change. They could have gone minus, plus, minus. And so we actually could have gone from no sign changes to 1, 2, 3, and we saw that pattern already. So what I want to show you from this is there's going to be one forced sign change for sure, but then there can be other accidental ones. So basically I call these two forced columns and these accidental columns. That's kind of how I'm going to be referring to them. Descartes' rule of signs essentially states two things about any polynomial written in descending order. That's important. Descending order of variable exponents. Uh, First of all, the number of positive real roots cannot be more than the sign changes. So the positive real roots are either the same as the number of sign changes or less. And if P is less, it's going to be less by an even number. That's basically what this says. I want to illustrate those with another example of what I was just doing. So if we follow the pattern again, we're injecting a positive real root. Basically, we're doing something like, this is supposed to represent that, and it just represents that binomial factor that produces a real root. It's basically multiplying that into, in this case, a polynomial with no sign changes. And so we do this times this times this, and we keep doing that till we get over here. This is what would happen if you actually had the variables and the coefficients in there. You see that we would have a definite positive here and a definite negative here. So these are both forced, but all of these could go either way depending on the size of the coefficient. So it could be just a single sign change, or it could be a bunch of sign changes. There has to be definitely one sign change because this and this are forced. So we went from just a positive to a positive and a forced negative. Now let's think about what could happen with these. So I call these forced columns and I call these accidental columns. They could go either way. So what could happen here? Well, let's make as many sign changes as we can. So let's pretend this had gone negative, positive, negative, positive, negative. So we went from no sign changes, we went from 0 sign changes to 1, 2, 3, 4, 5 sign changes. Actually, what I meant to say here was I want to look at the fact that there was one sign change, but it could be as many as five. So 1 to 5, maybe do this 1 to 5 sign changes. Let's think about why that is. So there was definitely, again, if all these had been positive, there would be at least one sign change forced. But then how many more could there be? And if you just kind of analyze this, really one thing we could do to make it easier to analyze the fact that the sign changes have to increment by 2 is, so we're going from positive to negative. We know that. So how many flips could happen in the middle? So let's just say this is positive, this is negative, and if I'm here and I have to get to here, well, how many sign changes could there be? Well, there could be 1, 2, 3, 4, 5 in this case. So it could be 1, 2, or sorry, 1, 3, or 5. And so we see they're increasing by 2. And that just emphasizes the fact that that's why the difference of the sign changes in the real roots is always an even number. And we saw that more in the beginning of the video anyway, a different way. So it's always entirely possible that you inject a single positive root into a polynomial and there will be at least one sign change, but there could be multiple ones just because of that one root. Look at another example where we're injecting a positive root into a polynomial with no sign changes, but it starts at all negative. So we would do negative times a negative, which is positive. Same thing here. This pattern would unfold. We would see that this has to stay negative. There's a definite positive added, and then again we have accidental columns in here. But what I kind of want to emphasize now is just the fact that if we look at up to here, we see that there were no sign changes, and just looking at this, there's no sign changes. What I want you to see is that the sign changes are always preserved in here, and then because of what happens with a negative times a negative creating a positive, this always has to be different from this, so there's going to be a definite sign change here. So we're going to keep seeing that pattern. Is the number of sign changes in here is at least preserved, and could be more because again we can always do that, but I want you to see that it's always at least preserved, and then with the additional sign change there's always going to be at least one sign change when you inject a positive root into a polynomial. Another example here, so I just made up a miscellaneous assortment of pluses and minuses, and so if we do the same thing here, negative times a positive, negative, 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 positive, 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 negative, positive, negative. And so let's look at all of them that are forced. Let's see, that one's forced. Okay, so that's all the forced ones. And so now notice that we had, if you look at the original polynomial here, we have 1, 2, 3, 4. So we started out with 4 sign changes. If we look at just the forced ones, for the new one, we have 1, 2, 3, 4, 5. So we went from 4 to 5, and that's not even counting the accidentals. That could add more sign changes, but we don't really care about that. Now, what I want you to see here so that this is more of a proof is why is this happening? So why does in this box the number of sign changes always gets preserved, or there can be more sign changes? But there is always going to be as many sign changes, at least in here, as there were in here. So this is 1, 2, 3, 4. We look here, 1, 2, 3, 4. Why does that happen? Well, so as we look at multiplying this negative times the pluses and minuses, what you're going to notice is if there is no sign change, there is no, this doesn't really do anything. It leaves it where it could go either way. But if there is a sign change, this creates another sign change. So between here and here was a sign change. I did negative times positive, it put a negative, and it created a forced sign change. And you're going to see that pattern just because of the nature of multiplication of negatives and positives. Every time the sign changes up here, this is going to force a sign change down here. So notice that these can all go either way, but here we have a sign change, and so this times this created a forced sign change here. So we go from positive to negative here, we go from negative to positive here. Then again, there's another forced sign change, and so that creates another sign change down here. And so that gives reason to why this is happening. And this would not happen, we're going to see later, this will not happen if you're injecting negative roots. So if you inject something like x plus 3 or whatever, and you're multiplying by pluses, exactly the opposite is going to happen. But we'll see that later. There can, of course, be more sign changes because of the accidental column. So let's put as many in as we can. So negative, positive, positive, negative. So how many we get? 1, 2, 3, 4, 5, 6, 7, 8. And if you think about that, we have to get from positive to positive. I'm just looking at these two. I want to illustrate again, I really want to emphasize that the changes happen in twos by even numbers. So we'd have to go 1, 2, 3, 4, 5, 6, 7, 8, and that all fits. We keep seeing that the positive roots are always going to be less than or equal to the number of sign changes, and if there's a difference, it has to be an even number.
Let's talk about what happens if we inject a negative real root. Is that capable of producing a sign change? So if you were to multiply a factor like this into some polynomial, and then of course this factor, would produce a root of negative 3. Can that produce a sign change? So we're looking at the fact that here that would be a positive number resulting in this, the second row instead of a negative. And so let's think what would happen. So we have no sign change. Now positive is very benign. It can't really do anything. It can't really make any changes. So we can see that, no sign changes. All of these would be forced to be positive. There could be no sign changes. Same thing with the negative. You'd have all these forced negatives. So at least in these two scenarios, it's not possible to force a sign change with the injection of a negative real root. So this one's a little more miscellaneous. So if I have this row here, it's going to result in the same row here. So let's think about what's forced. So this is forced, this is forced, this is forced, and this is forced. Um, so let's look at what's going on in here, not not looking at the extra term that materializes yet. So let's think about what happens when there is a sign. Well, first of all, let's count. Uh, 1, 2, 3, 4, 5. So there are 5 up here. How many are there here? It's just one. We see we actually lost sign changes. So why is that happening? Well, you'll notice that every place there is a sign change, it creates an accidental, which allows for the sign change to be lost. Every single place where there's a sign change, see, this results in this. So basically, you could kind of look at it like that. And so where there's a sign change, accidental. Sign change, accidental. If the sign doesn't change, then it forces a preservation of the fact that there was no sign change, but that's the best it can do. That it can do. Well, what if we make as many sign changes as we can inside the rectangle I drew? So plus, minus, and then this isn't going to help us either way. So we had 5 up here. 1, 2, 3, 4, 5. Okay, so the best case scenario is we could have this many instead of this many sign changes. And the clincher is that this will not ever be different from this. So you can't get a sign change from this new resulting term. Consequently, this is the result. We end up with possibly the same number of sign changes or fewer, and most likely fewer, as we can see. So in the injection of a negative real root cannot create a sign change like the injection of a positive root has to. What happens when we inject imaginary roots? So here I have a polynomial and I am injecting a pair of imaginary roots. They of course come in pairs, as you probably know if you're watching this video. If you were to set this equal to 0 and solve, then you would end up getting two imaginary roots, conjugates of each other. So now you might think, well, how can sign changes be caused with this plus? Because we saw with the negative real roots that that couldn't happen. But the pattern's totally different here because this is a degree 2 and it lines the the like terms up differently. This is one more over than it would have been with the negative real roots. And so it changes everything. Here my polynomial went from a single sign change to still having a single sign change, but this isn't accidental. So this is, it could have been negative, then we would have had 3. So we would have gone from 1 to 3. The important thing to note here, though, is that this doesn't hurt Descartes' rule of signs at all because the increments are by even numbers, and Descartes' only claim is that you're supposed to count the number of sign changes, and the positive real roots are either going to be that number or counting backwards by 2, any of those possibilities. So just because some of the sign changes are caused by imaginary roots, possibly, as well as by the injection of positive real roots, doesn't change anything. Doesn't hurt Descartes' rule of signs at all. So the important thing is this even number thing. So how do we know that the sign changes are going to be by even numbers? Well, so this pattern here, if you look at what's going on, you're basically ending up taking a row and placing the same row under itself removed by 2. So let's look at the forced ones here. So these are forced. This could either have been positive, so it would still be 1 sign change, or it could be negative, so it would be 3 sign changes. How do we know, though, the only important thing that the number of sign changes is going to be increments of 2, of an even number? So we don't even care what happens in here. All we care about is that if you place a row under itself, then if this was positive, negative, it's still going to be positive, negative. Whatever it was for the endpoints, it's still going to be the same thing. So we've seen this pattern before. If you know you have to get from positive to negative, and this was how the original did it, 1 sign change, well then if you add more, it's going to have to be 2 more, or 4 more, and so on. And it doesn't matter how you do it, you're still going to have the same thing happen. You're either going to have no sign changes or two sign changes or four, same with negative. So this is easy to see, very provable that the sign changes produced by imaginary roots have to be by even numbers. To sum up, positive real roots will definitely cause at least one sign change and maybe more by an even number. Imaginary roots can cause sign changes. It may or may not happen, but if it does happen, it will be increments of even numbers. And then negative real roots cannot cause sign changes at all.
Back to thinking of positive real roots and keeping Descartes' rule in mind, there are two special cases that I want to look at. A lot of times Descartes' rule isn't helpful because there's no way of really knowing just how many roots there are or if they're real or not. And but there are two special cases that you can always count on. Number one, if there are zero sign changes, there will be zero positive roots. Number two, if there's one sign change, there will be one and only one positive root. And really, those can be looked at as a proof, a rigorous proof, just looking at the graphs and using reason. So let's look first at the case of no sign changes. So looking at this, we see that the y-intercept is at 3, and there's no way this can ever go down. There are no negatives, so it has to go up. There's no way it's going to ever come down here and get a pair of roots. Looking at this, same exact thing. If we're already below the x-axis and everything's pulling down, there is just no way to turn and come up here and get a root. What about if there isn't a constant term? So we're at the origin. Same thing though, this can only pull up. It can't come down to the x-axis, and here the same situation. We're at the origin, everything's pulling down. So again, there's just no way to get a root on the positive side if there are no sign changes. You can have negative roots, but you can't have positive roots. Positive roots, I guess it bears mentioning, why can we have negative roots with no sign changes? And that's just because on the left side of the x-axis there are already negative numbers, and when they get plugged in, they're able to pull things across the x-axis. On the left side, you get even with no sign changes, you get both negative and positive terms when you plug in those negative x's, but that does not happen on the right side. Okay, let's look now at one sign change. So we see here we have one sign change, and my claim is that there will be one for sure and only one positive real root. So we're at this y-intercept, and everything else is pulling up. The only reason we're down here is because of this, and so it has to cross the x-axis, but then there's no way that these are ever going to give into this again. There's no way it's coming back. Over here we have two terms that are negative, and notice it's kind of the same situation, except from the y-intercept, this extra term is able to pull down a little bit, but then eventually these are going to win, and at some value of x, they're going to take this thing positive, and again, there's just no way it's ever going to come back. There has to be one real root, but there will only be one. It's never coming back. Let's look at a case where only the leading term is positive. And polynomials have the distinction of that the leading term, this is well known, the leading term at some value of x will always become more powerful than all of these terms combined. And that's because this being a higher degree, it grows faster, and so it's, even if it's not up with these at first, it will catch them, and once it catches them, then it will always overpower them from then on. It's never going to be weaker again. So from the y-intercept, these terms are powerful enough to drag it down for a while, but then there's going to come a point where at a big enough value of x, in this case actually less than 2, for a big enough value of x, it doesn't matter if you have really huge coefficients on here. The coefficients can never hang with the power of exponential math. It may take this term longer to catch up and pass, but it's still going to do it even with a leading coefficient of 1. And so this x to the 5 term, or whatever term is here, is going to have its way, which is why this term determines end behavior of polynomials. By the way, if you want a proof of that, I'll include a link to that in the description that I have. And because I didn't want to make this video longer than it had to be. So it doesn't matter if you have a bunch of pluses and then just this one's minus, or if everything is negative up to here and only this is a plus. This has to happen at some value of x. And again, since this term grows faster than all of these combined, once it reaches that value of x where it's bigger, it never again is going to be less. What if you just have a variable on the far right and you don't have a constant to start us out below and make us come up? In this case, we can see that the y-intercept of this is the origin. And how do we know for sure that this negative x will make this dip down, make it have to come back up and creating a root? Well, so I want to demonstrate to you that as you get close enough to 0, this actually becomes bigger than all the rest, just because of what happens when you put a fraction under an exponent. It gets smaller and weaker. So if you get close enough to 0, these are going to get very small and actually become less than this number. So you're going to have a bigger negative number at some point, making this have to dip down and then come back. How do we know that will always happen? So what I did is I created a little function here, c of x, for contest. I'm just calling it my contest function, and I'm pitting this number against all of these. And just to make it more interesting, I even put some big coefficients on there, because you might think, well, surely those big coefficients will keep x from being able to get bigger. But we'll see to no avail. Well, now all I'm going to do is divide every term by x, and we get a version that it's very easy to see that we can get the numerator bigger. We can make all of these x's small enough that they'll be less than 1. So for some x value small enough, we will have c of x greater than 1, implying that x is greater than all the other terms. So when we see this scenario, or it could even be maybe, the two far right ones are negative. It doesn't matter. But even just with this is going to have to be when close enough to 0. So here we're right at 0. Just after you leave 0, this has to be bigger. And so it's going to drag it down. That's going to happen every time. It's going to drag it down, and it's going to have to come back across and create a 0. The last thing we want to look at is the other part of Descartes' rule for finding negative roots. So to find the positive, you would look at your polynomial. So, pretend we can't see this. And you would count the number of sign changes. So 1, 2. So there's either 2 or 0 positive roots. If you want to find the negative roots, well, as we saw earlier, injecting a negative root has no effect on the sign changes. And so we can't use this test to find negative roots. So Descartes says, okay, take this and substitute negative x for all the x's. So you basically do this and then clean it up. So these are both this graph. And then you count the sign changes, and here we see there's one sign change, so it tells us there's one negative root, so these are positive, this one negative root. And so what are we actually doing? Well, that's where if you just remember that you can flip this graph, you can mirror it over the y-axis by doing this. That's all we're doing. So the thinking is, since we can't use this to find negative terms, what we're going to do is we're going to flip this around the other way, so it's like this, and we're going to pretend we're looking for positive roots. It's like we're on the back side of that graph looking at it, and we apply the same test then that we did for positive roots, but we know since we flipped it around into a mirror image, we're really looking for the negative roots. And so that's why we do this procedure here. It can seem really mysterious until you understand we're just flipping the graph end for end so that we can apply the same test. So that's the end of my video. So we looked at Descartes' rule. That basically is, it's mostly summed up just by these facts, that the number of positive real roots are always equal to or less than the number of sign changes, and when they differ, it's always by an even number. So if you were mystified by Descartes' rule of signs, hopefully this helped.